Okay, welcome back. We're now going to commence our discussions of basic heat treating principles and practices. And so we're going to start off really with a really nice definition, a very thorough definition. And so we're going to get started with that. Heat treating can be defined as the controlled application of time, temperature, and atmosphere to produce a predictable change in the internal structure or microstructure of a metal. So let me write that down for you. The controlled application of time, temperature, and atmosphere to produce start the clock there to produce a predictable change in the internal structure, which we know would be called a microstructure of a metal alloy. So that's what heat treating is all about. And we're going to talk about, there are three basic principal heat treatments that we'll discuss. But what are the reasons or the purposes for mechanical or for heat treating? Benefits and reasons for heat treating. Benefits and reasons okay. Basically, they are there to help control and or enhance basic mechanical design properties of metals. All right, so the reason we do it is because standard plain carbon steels just have sort of a limited role in what it can do with respect to design specifications on different critical components and structures and pieces and parts. And so we are able to manage the potential properties of steels through these basic heat treating practices. And so it allows us to gain certain specific specifications relating to the metal's properties to obtain that design performance for that particular component. And it all really goes back to, in essence, the allotropic element iron. And we'll talk a little bit more about that later, of what it can do. And we know what allotropy is, meaning that it can change its crystalline structure. That's the whole basis for this. Okay, so some of those properties, of course, the most obvious one would be hardness. All right, another property that's susceptible to this would be a ductility. Ductility. And let's see, I'm going to change pins. These pins are, if I can find another one. Ductility, of course, strength is a big one that we can change and alter. Toughness, of course, another good one. And last but not least, some of the internal or residual stresses. And most of the time what we're trying to do there is minimize some of those inherent residual stresses that occur in the manufacturing or the forming of these parts and components. Okay, so those are the basic material design properties that heat treating affects, and usually giving it an enhancement to those properties, or actually just manipulating and managing those properties to our benefit, to what we need to have that component, what kind of properties and performance we need out of that component. We can do that through these heat treating practices. So let's look here, and what I want to do now is essentially look at I need to get another pen because these things are not working very well. Actually, none of these are working very well, but that's okay. Okay, so let's look at the three principal sorry about that. Three principal heat treatments. Oops. Three principal heat treatments. All right. Now, let's start with the first one, which is the most obvious. It's hardening, but it's specifically called through hardening. Okay, through hardening. Through hardening. The next one is called surface hardening. Surface hardening. And the last one has nothing to do with hardening. It's more about softening. And so we call these softening. Process. So we've got through hardening processes, surface hardening processes, and softening processes. Okay, so let's detail these out a little bit. Under through hardening, we're going to have basically, this is just the complete hardening all the way to the core, the complete volume of that part completely hardened. That's what through hardening is about, sometimes referred to as deep hardening. But that essentially is taking something like this, okay, a solid piece of steel that looks like this, and it actually started off as just a solid bar, and based on what we talked about this morning earlier about machining, we took and put this in a more than likely a CNC turning center, and we removed all this metal from that solid bar to get this geometry profile, this shape. Okay, so let's say this part needed to be completely hardened all the way through to its very core, all the way through, completely hardened. Then we would go through what we call a through hardening process, which basically in all hardening processes we're talking about heating the steel up, which is called austenitizing, and I'll get into that in a minute. And then the second step simply is just quenching it or cooling it down. So this would be an example of a through hardened piece, something like that. All right. Now on surface hardening, we've got a couple of these surface hardening processes, what we call diffusion. These are basically taking advantage of Fick's first and second laws on diffusion. So these are diffusion treatments. Diffusion treatments, okay? I ran out of space there as usual. Diffusion treatments. And essentially what we're doing is we are putting or diffusing carbon in or nitrogen into the surfaces of these parts. And so they're generally referred to as carburizing. All right. And under these, we have a couple of examples. There's something called pack carburizing. And the pack carburizing can be broken down further as to what kind of heat we're using. We can either use a flame, usually an oxyacetylene type of a flame, or we can do it with a gas, and this gas would be something like nitriding or carbonitriding. So we can do it two different ways. So, all right. Now, excuse me, I got off on that. Sorry. The gas would be the flame, of course, or we can heat it up through induction. Induction through electrical current. We can heat this thing up for the purpose of austenitizing the steel. Then the other one is called gas. And instead of packing solid carbon particles around the component and then heating it up, now we just expose it to an elevated carburized gas or nitrogen gas, and do it that way. So those are the two different types. So again, surface hardening are basically diffusion treatments, which are referenced as a carburizing, because we're just diffusing carbon into the surface to a certain thickness. And we can do that one of two ways. We can do it a pack carburizing, which is basically dry, solid carburizing, or we can do it through a gas, okay? And if we do it through the dry method, we use two ways to heat that up, and that's with either a flame, oxyacetylene usually, or an induction or electrical current, okay? And then finally, to the softening processes, basically what we've got here is, generally speaking, overall, can lump it into what we call annealing processes, and then also something we'll refer to a little bit later called tempering. But these are all basically softening processes. So those are the three principal heat treatments that we're going to be discussing in detail here as we go through this. Okay, so let's look at, let me erase some of this stuff right quick. About these, oh man. All right. Okay. So let's look at this through hardening right quick. This first type we talked about. Through hardening. Okay. Again, we're just trying to heat something all the way through and get it to a certain hardness to it. And it's two steps in that. Step one is what we call austenitizing. Okay, that's the first step in any heat treating. Well, in through hardening specifically, we call it austenitizing. Austenitizing, which is basically just heating. Now, when we austenitize it, that's a specific temperature, you see, because austenitizing means that we're going to bring up that temperature. Let's say we have a hypoeutectoid steel, and if you allow me to draw the diagram right quick here, this is kind of what it looks like. if you recall, let's say we have a and this is at 0.8%. Let's say we have a 0.6% steel here. We come up here. Well, the austenitizing temperature is always going to be this upper transformation line, or this just above the A3 line in this case, about roughly 50 degrees. So this is going to be plus 50 degrees above its A3 temperature. All right. And again, that is found back on the iron-carbon phase diagram here. So that's the austenitizing temperature. All right. Now, why is it austenitizing? Because this is when the ferrite goes from, a BCC structure up to an FCC structure. All right. So now we have this into an FCC structure. Okay. Which is what we want. We always start any through hardening process by bringing it up to that austenitizing temperature, so we can gain access to this crystalline structure, because we know there's so much more opportunity for interstitial sites for carbon to get into, and that's what we're trying to do, is maximize the interstitial sites for carbon. And I found this wonderful little diagram here that shows that. Of course, this is an FCC, face-centered cubic, and these large circles in here, these are all the iron atoms, okay? All these little red dots are all potential interstitial sites for carbon, okay? And so you have, there goes the timer. So you have much more possibility of having carbon atoms, interstitially speaking, in this FCC lattice site as you do in a BCC lattice site. So this is why we want to always start, if any through hardening process, bringing that thing up completely, all the way through. We let it soak, let that component soak, and get it to that just 50 degrees above the A3 temperature, wherever it is, composition-wise here, and so we can maximize the carbon absorption in that FCC lattice. Okay. So that's what that's about. So once we get it there, then the second step, of course, is always just to rapid cool it, or what the terminology is called quenching. And that's just, again, rapid cooling. Rapid cooling. And of course, the three basic ones are, in order of aggressiveness, brine is first, and then water, and then oil. Okay, those are the three basic quenching medias that we use. So that's the process, two-step process. Austenitizing the steel like this, and then immediately once it's austenitized, we quench it. We put it in a tank filled with brine, water, oil. We agitate it and let it cool down as quickly as we can. What we're trying to do is capture all of those carbon atoms that are in FCC, so that they don't precipitate out or diffuse out into perlite or anything else by a slow cool. And so when we do, we capture all those, and we go under another transformational crystalline structure change to a body-centered tetragonal, which is a product we call martensite. And we'll look at martensite in specifics when we get to the IT diagram, or the time temperature transformation diagram. We'll talk about martensite and how it forms. But that's the whole goal here. All right. Now let me throw this in here at you too, because this is all of this austenitizing and quenching, the hardening process here, is something we call allotropic. And it goes back to iron being the allotropic element, as I mentioned a moment ago. The allotropic transformation, allotropic transformation quenching. So that says it in a nutshell. That's all these two steps. Allotropic transformation quenching, or you can just say ATQ for short. Okay, but that's what's taking place on this through hardening, or any hardening really. So this is the mechanism by which steels are hardened. This is the mechanism. We can label this mechanism for all hardening takes place through an allotropic transformational quenching. All right, which are basically these two steps. Okay, so I'm going to have to stop this, and we're going to have to pick it up here in just a little bit after I get this uploaded, and we'll start in on the surface hardening process, and then a little bit the annealing, and then get into the IT diagram. So we'll see you on the other side.